Which is good, because I'll keep you looking over there.
Yeah. So it's hard.
Yeah.
Let's get down.
You can.
Right.
Ouais, on y va? OK. On va fermer celle-là, puis les gens se... Non, celle-là, tu peux la laisser ouverte. Vous attendre, Kat, qu'on ait fini l'introduction. Ouais. Bonjour tout le monde, merci d'être là en grand nombre. Aujourd'hui, on est très heureux, très fiers d'accueillir Anthony D'Amato. Anthony est professeur agrégé en sylviculture et écologie forestière à l'Université de Vermont depuis 2015. Il est aussi le directeur du programme de foresterie là-bas. Avant ça, il était professeur adjoint et agrégé à l'Université du Minnesota. Ses recherches visent à comprendre la réponse à long terme des écosystèmes forestiers dans un contexte de changements globaux. Anthony a largement contribué à l'utilisation de la sylviculture comme outil d'adaptation face au changement climatique. Il va beaucoup nous parler de ça aujourd'hui. Il participe au développement de solutions pratiques face au changement climatique, notamment en testant l'efficacité du traitement sylvicole face à la sécheresse. Anthony est un chercheur qui est reconnu internationalement avec à son actif plus de 90 publications scientifiques. Donc, on est extrêmement heureux, encore une fois, d'accueillir Anthony. Bien sûr, la conférence d'Anthony va être en anglais. Anthony told me that it will try to speak slowly.
Yeah.
Sure. You'll do something? Okay.
Feel free to stop me, too.
Okay. Okay.
Thanks, Philip. Thanks for the opportunity to be here. As a few folks know, this is my second time in Quebec in a week, and much of this talk a few of you've seen, but I saw Philip last week. He told me, well, you have 1 week to improve your talk until you come visit us, so hopefully it's an improvement and a few extra things. What I'll be talking about today is some of the work that we're doing around looking at silvicultural strategies in the context of global change. And so I'll go through just some context that most of us are already familiar with in terms of how folks are looking at global change in northern forests, and then get into some of the ways we're looking at kind of building on our past understanding of forest dynamics as a way to inform adaptive silvicultural techniques going forward. And as Philip said, if there's anything that's unclear, feel free to stop me. I'm happy to try my best to explain that and slow down. So as we like to think about in terms of management, really we're moving into an era that we call this era of novelty, uncertainty. And there's several elements to this that really make it challenging for us to make management decisions with really much certitude in terms of how things might play out in the landscape. And a lot of the emphasis, certainly across the globe, has been around global change, and even here in the Northeast, this is an example from 2016 of a drought that also impacted parts of Quebec, where we're starting to see these extreme precipitation events, both low precipitation, but also very high precipitation events in very short periods of time. At the same time, we're seeing an increase in the amount of extreme wind events, ice events, snowstorms, even on the ride up. Got to see some ice from last night, so certainly trying to manage in the context of those dynamics. But also, I think something that's always worth pointing out, and that's somewhat unique in a negative way, unfortunately, for the Northeast, is that we also have the great misfortune of having the highest density of non-native insects and diseases of any really part of the globe. And there's a great paper that some of you have likely read by Gary Lovett, where they estimate on average we gain about 2.5 new non-native insects every year, 1 new wood borer every 5 years coming into the US. And so not only are we dealing with uncertainty about how future climate conditions are going to affect our forests, but also every week there seems to be something else that we're concerned with, and certainly here, both in Quebec and in the Northeast, species like the hemlock woolly adelgid, Asian longhorn beetle, and emerald ash borer certainly give us quite a bit of pause as to how our forests might change over time. But what I like to certainly bring up quite often is where we've come from. I think there's a tendency in silviculture and in science to really jump onto the new and kind of forget the old, in some cases pick on the old. And when it comes to looking at where we've come from in terms of our management and the science guiding our management, we've really just experienced an amazing 3 decades of science around ecosystem management, understanding how natural forests work, and using that understanding as a way to inform our silviculture. And again, many of you certainly, hopefully, are at least familiar with these 2 books that were really influential in Quebec and elsewhere, but also certainly other books around the globe that really have looked at ways to understand natural forest dynamics and use that understanding to build into ecosystem management. And the challenge with this is I've just been describing very novel and uncertain conditions, and so many now say, well, we can't really rely on the past anymore because that will never occur again. And what I'll argue to some degree as we go through this is that we can gain a lot from building on our understanding of ecosystem management as a way to enter into this new era of adaptation. So what we've seen, certainly from the US side, and I also pay plenty attention to work in Quebec and elsewhere, is that a lot of the emphasis of new science around climate change and understanding future change in forests has really shifted from this focus on the past and understanding natural systems to really focusing on finding different ways to forecast the future. This is an example, and I know you have similar ones for Quebec and across Canada, of what we call the tree atlas. It's for eastern US, and it's based off of our inventory data. And what it basically is a climate envelope model for different species. This is for red oak, just showing what we expect to be the future kind of change in habitat availability for that species in the future under a high emission scenario. And so the blue colors here are reflecting places that would gain habitat, and then the hotter colors are places that would lose habitat. And also, as you all know, in 100 years we'll have that wall built around, so no oak will be escaping the country. So certainly looking to the future. Also, in an empirical sense, a lot of mesocosm studies. So this is an example of a warming experiment where folks are trying to simulate future climate conditions, and I'll mention a mesocosm study later on as it relates to drought conditions. And so the shift away from really looking at kind of ecosystems and focusing pretty heavily on just what species should I plant where, what species are going to do well in the future. So we've gone from this kind of whole ecosystem emphasis to now really focusing on tree species and what species make the most sense. And what that's really shifted from a management perspective, at least in various circles, although I know there's certainly work being done here that has a more holistic approach, is that a lot of the recommendations as it relates to adaptation to climate change are what species do I need to plant or what genotypes we need to plant. So we've gone from a time period where a lot of our emphasis was on trying to manage for complex ecosystems, managing for a diversity of structures, a diversity of species, to now really focusing on making sure that we're putting the right species out there in the landscape and not really focusing much on how are those going to be arranged and how do they fit into the actual processes in that ecosystem. So a major shift in the last 10 years or so. So the problem with this, and one that I think I can say with fairly good certainty in our temperate forests, is that even though we're seeing a lot of stress on our trees, both in terms of drought, disturbance, emerald ash borer, Asian longhorn beetle, general projections suggest that our trees are not going to disappear anytime soon, and we're still going to have a lot of our species like sugar maple on the landscape. And so when we're looking at integrating adaptation into our forests, and again, much of my perspective comes from north temperate ecosystems, we're likely going to be integrating adaptation into existing ecosystems. It's not this wholesale change that's going to occur. And I often like to say that these sugar maple are not looking at those climate projections. They're doing what they do and really withstanding a lot. And so when we're trying to look at integrating adaptation into these systems, we should be building on our understanding of how these ecosystems function. Beyond an ecological perspective, just from a social perspective and a communication perspective, many of our managers, this is the context with which they operate in. And so when we're trying to think about integrating adaptation into what they do, it makes a lot of sense to meet them where they're at and then build from that versus saying we totally have to change everything and begin planting new species. So many are familiar with this, and especially a few folks from last week and beyond. This was talked about a lot as it relates to adaptation. This figure is from a paper that Linda Nagel led in the Journal of Forestry, but really is building on Constant Millar's paper in ecological applications from a decade ago, where she really laid out 3 different kind of options as it relates to adaptation. And the reason I like this figure a bit better is that this really is a continuum where each of these strategies builds on one another. And so again, I know most folks are familiar with these categories, but the way folks are envisioning strategies for looking at adaptation is that in its lower end, we have resistance, where we're really trying to manage to the best of our ability to withstand change, doing as much as we can to minimize stressors, minimize what we might see for drought impacts, and really try to improve the defenses of that forest against future change. And I really view this as the high input and low likelihood over a long term in terms of our ability to sustain that strategy. Moving along the spectrum, again, resilience, we're really looking at, and again, I know many of you are familiar with the concepts of resilience, where we're building off of aspects of resistance, but we're also integrating some elements that allow that forest to respond to change in a way that might allow it to have mechanisms to return to whatever our prior desired condition might be in that ecosystem. And then finally, transition, which I'll talk about later in this talk, and really the place where we have the most uncertainty around what to do and how to do it as it relates to forest systems. But in this case, what we're doing here is using the best available science about future conditions and managing deliberately to try to shift that forest towards a condition we think might be better able to respond adaptively to new change. So I'm going to first talk a bit about resistance and resilience strategies, and then we'll towards the end I'll get into transition, where we're really trying to figure out the best way to do things in the landscape potentially. So what we're going to go through are a couple of examples of some work we've been doing. Those in the room that do work in forest management know as it relates to planning for climate change and it relates to the uncertainty around that, it's really a challenge from a manager's perspective to get folks to make drastic changes today, because there's a lot of risk involved, certainly in terms of making the wrong choice in terms of species or the wrong management decision. And so I'll first talk about some work we did where we looked retrospectively backwards to see how effective certain strategies were in the past for withstanding some changes. And then again, I'll end by talking about some newer experiments we're doing where we're looking at kind of transition and adaptive management in that context. So what I'm going to dwell on right now is just an example of kind of a classic resistance or resilience strategy around density management. Those of you that have been fortunate enough to take a silviculture class, best experience of a college education, know that thinning has always been talked about as a way, so reducing the density of forests as a way to increase resources available to residual trees. And so as adaptation has come out and folks have thought about how do we adapt to future extreme events, particularly droughts, although this has also been recommended for certain insect outbreaks, that can we do things like thin forests as a way to minimize the impacts of extreme climate, and particularly, again, drought events. So we certainly talk about this a lot, but there hasn't been a lot of kind of at least empirical evidence that this works. And so we wanted to actually evaluate this retrospectively. But one thing that's worth pointing out is that when we look at the life cycle of a forest and also a silvicultural system, this is really working with what's currently there and trying to kind of maximize its defenses against drought. But really a long-term adaptation strategy might be over time to shift this forest towards species that might be better tolerant of drought conditions. So this is really a near-term strategy to keep that forest able to defend itself against drought. So to do this, we've been working across, similar to Quebec and similar to the rest of Canada. The U.S. Forest Service has established these long-term experimental forests. Actually, the oldest one is this Fort Valley experimental forest in Arizona. It goes back to 1917, so very old experiments. But there's several locations that we were able to get access to, and our goal there was to take advantage of this rich history of management. We know the history of these forests. We know when they were thinned. We know what the treatments were. There's every 5 to 10 years, all the trees are measured. And our goal with these areas was now to go into them and collect increment cores from all of the trees in those plots, because we wanted to not only be able to look back every 5 to 10 years, we want to be able to look at these forests with interannual resolution. Every single year, how has this forest been growing retrospectively? And our goal was really to look in the past at historic events, both droughts, insect outbreaks, to evaluate, are there some evidence from historic extreme events that certain management regimes were more effective than others at withstanding those impacts. So just to, in a nutshell, show kind of the type of data that we're using, we're coring all of the trees in the plot. So those of you that are familiar with dendrochronology, oftentimes folks will select a few trees and core them and use that as representative. We're interested in population level response to historic events. So we core everything and then use that as a way to kind of back construct. So this is for one site, interannual variability in kind of population level basal area increment. Of course, it's net basal area increment, but at least an ability to look at specific years. And then what we do is kind of look at a given year that we know there was an extreme event. So in this case, we knew there was a very extreme drought in 1988. How did that forest grow relative to other densities in that stand? So I'm just going to show one example of some of the work that's come out of this. We've been using this data for a long time because it takes we record a lot of trees. We want to get a lot out of the data. But I'm just going to focus in on some work that Alessandra Botero did, where she was really examining this aridity gradient we have in our data. So ranging from very arid forests in Arizona to more humid forests, although these would feel pretty dry to us here in the Northeast, but they're pretty wet if you're from Arizona. And really looking at how these have responded to a range of densities historically, and is there evidence that density management and lower density stands potentially had more resistance or resilience to drought. So we had a paper come out in Journal of Applied Ecology a couple of years ago, and I'll talk you through these graphs. So the 3 different locations: Minnesota, South Dakota, and Arizona. So humid, dry, very dry. And then the y-axis is actually an index of resilience, which really is representing kind of how well that forest was able to rebound and grow at levels prior to the drought. So if it's above 1, that forest actually was growing kind of either the same or better than it did during the drought. If it's below 1, that forest actually never was able to recover its growth rate during that drought event. And then what we have on the x-axis, this is just percent stocking, so percentage of the maximum stocking based on stand density index. And then 2 different drought events. So when the stand was younger, so in this case when this stand was 50 years old, then when the stand was 100 years old, to look at just how that drought response changes over time. And so looking at just the general trends, obviously as density increases, resilience decreases, particularly in these arid systems, but also as these stands get older, you notice the y-axis in particular for the dry sites, but even for the Minnesota site, the level of resilience actually goes down as these stands get older, so the ability for them to respond and recover actually decreases. So we had to prove it, but anybody would have told you 7 years ago, thinner forest is probably good for density management. And just to drive that point home, this figure here, and I know it's a little bit washed out with the lighting, what we did was plot, based on historic data of mortality and growth reductions, those density conditions that actually were vulnerable to drought. So in red here, this red band and then this red band, those correspond to density conditions where the forest was actually experiencing growth reductions or high mortality. And this blue band corresponds to those conditions where we saw low mortality and actually, high resilience and resistance. And again, those that study silviculture should say no surprise. The areas that we always recommend to manage for, which are right here, tend to be actually the ideal conditions in terms of minimizing drought impacts. And as you would expect, as stands get denser, we see kind of greater growth reductions, more mortality. But also, at least in this one site, very open stands. These forests have been maintained at 7 square meters per hectare for over 50 years. So those trees were very large, but very open. We found that those also had higher levels of mortality during drought, both because the individual tree experienced a lot of physiologic stress, having that high leaf area to sapwood area ratio, but also because they're open stands, and so there's much more kind of loss of water from the soil because there's more direct solar radiation. So to take this a step further, because we had cored all of the trees and we also know the history of these forests, we were interested in looking at kind of individual populations of trees that had very different histories to understand if there was any difference in their sensitivity to drought. Their sensitivity to historic climate. So what this picture is showing you is just 4 different densities ranging from very low density conditions to our unthinned control. It's just the basal area of those plots. And these have been maintained at those basal areas, those densities, for over 50 years. And so what we did was look at, using response function analysis, the growth-climate relationship between trees and these different populations to see what were the most important monthly variables for driving growth. And surprisingly, even though it was the exact same species, the exact same site, exact same age, depending on the density of that forest, the trees had very different responses to climate historically. And so these low density stands were only sensitive to actually the previous year's fall temperature. So if we had a warm fall the prior year, they often had smaller rings, which basically was suggesting they're expending carbohydrates before they go into dormancy. Whereas as we increased in density, we not only saw the importance of these temperatures, but also precipitation. And the reason why that's important is as we think about changes in climate and how it's going to affect different species, a lot of the emphasis is just saying, well, this is red pine, it's going to be a climate winner, or it's going to be a climate loser, or this is red oak, it's going to be a climate winner. And what I really get concerned about is this single species narrative that we just generalize for any given species that is in trouble. But what this is showing is that even on the exact same site, same species, depending on how it was grown, had very different responses to climate. And so linking that back to how we think about our historic period of ecosystem management, we've been emphasizing for a long time the value of diversity of tree sizes more from an ecological complexity standpoint and from a diversity standpoint. But what this is suggesting is that when you have a complexity both in tree sizes as well as their densities, that's also giving you complexity in climate response, even at the stand level, within the same species. So giving you that variety that's quite important. Just to take that a step further and translate that and link it to some of the ecological silviculture techniques that have been suggested over the years. This is an aerial photo of a red pine forest in north central Minnesota. Here they're doing kind of a mix of different retention patterns as part of ecological silviculture study. And then this picture in the inset is also a very young red pine forest where they're doing what we call variable density thin to try to really restore some spatial complexity. So try to restore some ecosystem complexity to that forest. So these techniques were really designed, again, many in this room are familiar with this, to restore some complexity for biodiversity conservation purposes, to try to create more heterogeneity in habitat conditions. But if we look at this within the context of climate change adaptation, there's also a lot that we can link to this in the conditions at the stand level that this creates. These individual trees, historically, we might retain as a distributed source of mature habitat, so from the traditional biodiversity standpoint. But through the eyes of looking at this from a drought perspective, these are the trees that we likely might see lower drought sensitivity, right? They're in lower density conditions. At the same time, if you're in fire-dependent communities, that might also have obviously lower vulnerability to ground fire. But these are the trees that you might see that go down first in a windstorm, right? Just they're more exposed. On the flip side, and I'll talk more about this in some of our work, we've talked a lot about retention of these aggregates, so leaving these clumps or groups of trees out there as permanent reserves. And again, from the perspective of historic thinking about biodiversity conservation, although I know these aren't, it's not interior habitat, but nonetheless they might provide micro-refugia for species that need at least some shade on the microsite. But also these are going to be higher density areas with more drought sensitivity, but lower vulnerability to wind and also greater selection pressure. So giving you kind of a different perspective there. And then finally, these gaps, so these openings, might be the places where we actually can have adaptation occurring through new species and other things being integrated. And so again, the reason I'm bringing this up is that this is a technique that was developed, I guess we'd now call it old forestry. It was new forestry 20 years ago. And the goal was all about biodiversity, but there's a lot of ways of looking at this landscape within the context of adaptation as well, without major changes to the prescription. So just to continue along this lane in terms of thinking about variability and climate response, just another example of what we've been doing with retrospective records. We collected over 3,000 individual tree samples of increment cores across northeastern Minnesota. So these very mixed forests ranging from temperate to boreal ecosystems and right along Lake Superior. And we're interested in trying to understand what have been the important historical drivers of growth in these populations. And so traditional tree ring work would strip out all the noise associated with tree size and age, but we want to carry that noise with us because we work in forests and that exists in forests. And so we were interested in trying to understand what's the range of response for any given species in terms of its climate response. And so as an example, this is the posterior distribution for the variance function for how these trees respond to the temperature. And so each of these is just the acronym based on the species, the genus and species, so Picea mariana, Picea glauca, and so forth for different species. And when we looked at actually the level of within species variation in temperature response compared to the between species variation, we often saw there was much greater variation within a species than between. So again, speaking to the fact that we can't just say northern white cedar's in trouble, there's a lot of variation in that species, and what we were seeing is that it was largely being driven by differences in size and differences in age, and so trying to build off of that understanding. So certainly a critical component. So I'm going to finish with one final kind of element of just this complexity and get into some new experiments that we're doing now as we relate to this. So just to prove that I'm a hypocrite, we are doing mesocosm studies and using them as ways to think about the future. Although I guess the twist that we're taking on these is we're very interested in germination of different species. What we tend to see in many cases in these warming experiments is that people will plant seedlings and then say this is the future forest, and all of us know you just skipped the biggest bottleneck in the tree's life, which is going from seed to seedling to established individual. And so we've been interested in trying to understand how different species that are projected to do well in the future might respond to projected changes in precipitation. And similar to Quebec, in other parts, certainly going into the Maritimes, there certainly are some projections that we're going to have future droughts, but there's also projections that we're going to have future heavy rainfall events as kind of the common regime. And so this experiment is it's a mesocosm. We have it replicated 3 times. And we're looking at 4 different precipitation regimes. There's no climate temperature modification. And so the control, all we're doing is looking at, we're delivering the average volume and frequency of rain that we've experienced over the past 100 years, kind of what's kind of been the 100-year baseline for frequency and amount. The drought, again, we're not living in Arizona. Basically, again, by varying frequency and amount, it's a 55% reduction in what is projected. And again, this is based on projections, at least for this portion of Vermont. We have an episodic treatment, so this is really what a lot of folks are saying is a likely climate scenario, although precipitation, as you all know, is harder to predict than temperature. But generally, there's an expectation that we're going to get very infrequent but large rainfall events, so we'll get our doses in large quantities. So what that ends up doing is over the entire growing season, reducing the total amount of precipitation by 21%, just based on, we get a lot of rain and we don't have rain for 2 weeks and we get a lot of rain. Then finally, there are some projections that we're going to have just these very frequent large rainfall events, and so we're looking at 83% increase. I'm not going to talk a lot about this experiment, just to show one element again, as Philip likes to see me prove silviculture over and over again. One aspect of this experiment is that we see a lot of models about migration and species migration potential and where they're going to go. One issue with those models is they assume the closed canopy forest isn't going to be there. But the other issue is that they assume substrate availability is going to be perfect. And so what we wanted to do is look at differences between litter substrate and then mineral soil substrate within this experiment. Again, all of you that are ecologists and silviculturists know mineral soil matters, certainly for a lot of our species. And so just to drive that point home and highlight that it's beyond just the complexity of species response, obviously substrate response matters a lot too. I have just taken the white pine and the oak data from the first year of germination in this experiment, and one broad take home again, proving decades, if not centuries of silviculture, mineral soil matters a lot to these species in terms of getting established on stable substrate. But looking at white pine as a species, the control again is our current precipitation regime. And we generally see lower germination of that species regardless of substrate once we start getting into these droughtier conditions. But then again, it peaks up once we start having very wet conditions. So for us, certainly some concern over white pine. I know you might be gaining more white pine in Quebec. Whereas red oak, species that most folks view as a major climate winner, substrate is going to matter dramatically to the species. So when we look at kind of future dynamics, it's not just as simple as saying it's going to migrate and be everywhere. At least from this work in mineral soil, and these sites are a little bit coarse textured sand, so it does very well even under the inundation conditions. All right, so I do some mesocosm stuff, but not a lot. So what we'll talk about to finish here is a new experiment we're doing. These are very preliminary results, and I've added in a bit more detail actually based on Frederick's comment about how we develop these treatments. But there's a lot of interest now in designing operational experiments. And I know folks here in Quebec and in this room are working on these as well to try to understand how do we integrate adaptation and move forward with some new experiments. So what I'll be talking about is the Adaptive Silviculture for Climate Change project. Right now, this is largely a U.S. project, but I know there's going to be some installations in Canada coming forward, so there's been discussions about that. But right now, this was started by the U.S. Forest Service. I showed a map before of all those dots that said U.S. Forest Service experimental forests. That was the first period of co-development in our nation's history of managing forests, and a lot of folks are viewing this as kind of the next wave of long-term studies to look at kind of future issues in terms of silviculture. So the Adaptive Silviculture for Climate Change project right now is in 5 locations. Linda Nagel is the lead of this entire network. She's at Colorado State University. But then at each local site, there's lead PIs. So I lead the site here. I'm in northern New Hampshire, and I'll be talking more about that in a moment. And I also am a co-PI on a site in Minnesota. And really the goal of these is to develop these studies that are co-produced, and I'll talk more about co-production and how we do that, but really working with managers to integrate their concerns about climate change, but also integrate their perceptions and perspectives on how might they best manage for some of these threats, versus us just sitting in our office and saying, here's the strategy, take it. Trying to actually get them to give us input on what might make the most sense. And what's also unique for the US, in borrowing a lot from what you've been doing up here for a long time, is we did not do a very good job of making big experiments and replicated experiments a long time ago. So trying to actually build, by our perspective, you'll see there's still baby experiments compared to some of the things that are happening up here, but some larger studies that will allow us to look at multiple response variables. So in terms of actually how do we design these experiments, what does the co-production process look like? The way this is being developed is a bit different than kind of your traditional long-term experimental study. And so the co-production process or co-development process has become a big point of emphasis for a lot of natural sciences in the U.S. Really over the last 10 years, there's this term actionable science that's a very common buzzword. But more and more they're looking for kind of these studies that actually bring in a manager's perspective to work on this. So at each of those locations I just showed on that map, they held a 2-day workshop that really entailed 2 components of what we do a lot in our daily job. And one component was to look at vulnerability, and so they brought in climate scientists, forest health experts, forest ecologists to really talk about, at this location, these are the threats and these are the projected changes. And so got everybody on kind of the same page in terms of what the vulnerability was of that ecosystem. And then once that was done, actually went out to the site with the managers and talked through, these are where the experiments are going to occur. What are some of your concerns operationally? How would you traditionally manage this? And how do we possibly work with the site? And then very importantly, and again, something that's no surprise to this group, given the interdisciplinary work that's done here and across Quebec, not just having forest managers, but also wildlife biologists, hydrologists, also folks representing a cultural perspective, so that we're getting kind of a holistic view of that ecosystem and viewing vulnerability not just in terms of impact on trees, but also some of these other values that folks might have for that area. So this study has 3 treatments: resistance, resilience, transition. They used to call this response. It was always nicer having 3 R's, but now we had to add a T in there. And the way this worked was they paired up the scientists with the managers. They sat in the woods together with worksheets and went through, what do you want this forest to look like in the future if you were to resist change? And so as an example, this forester said, I want this forest to still be able to produce 0.4 cords per acre per year, no matter what the change. I want the basal area to be anywhere between 16 and 18 square meters per hectare. And then from the hydrologic perspective, we want to have stable flows and so forth. Based on those desired future conditions, then we had specific objectives related to kind of what they were interested in from that ecosystem. And then finally, the fun part was how would you actually do that? And very specifically, what's the time frame? Kind of how are you actually going to accomplish this in the landscape? And so this resistance, resilience, transition, again, those broad categories were applied in 5 different locations and look completely different depending on the ecosystem and the manager. So really trying to localize it to that site versus applying the same treatment everywhere. So the experiment I'll talk about, and again, very, very preliminary results in terms of what's happened, is on the second college grant site. So again, northern New Hampshire. I know many of you are familiar with Dartmouth College. You might not be familiar with that. They do own a lot of forest land in both New Hampshire and in Vermont. In particular, they have a 10,000 hectare parcel of land they call the second college grant. It was actually granted by the state of New Hampshire in 1807. So they've had that land for a very, very long time. And it's northern hardwood forests that we're working in, but there's certainly mixed woods and elements of mixed wood, even in the areas that we're doing the experiment. Again, it's not very extensive in terms of across a wide range of sites, but within this landscape, we have kind of 4 replicates of the experiment in these 40 hectare blocks. And so we have a range from resistance to resilience to transition, and I'll talk more about what that exactly is in a moment. So this has been on the ground for a couple of years now. So in terms of those treatments and what do they look like, again, Philip, I could get a quiz on this. He's seen this a few times, as is Frederick. But in terms of what these treatments look like and how they were translated from kind of the manager and scientist perspective into tactics on the ground. Resistance, again, trying to keep this forest as a northern hardwood dominated forest, closed canopy, uneven age, all those things that we characterize many of our northern hardwood forests, certainly in the States and in parts of Quebec as well. So single tree selection, kind of classic approach to maintain that dominance and kind of typical stocking levels. One element that came up a lot talking with the managers was their concern over extreme precipitation events and erosion. And so we increased the amount of dead wood in that forest and actually deliberately felled trees perpendicular to the slope to try to at least maximize water storage on the site. And we're doing a lot of work with dead wood in the forest. And then also when they're selecting trees as retention trees, so the residual trees, favoring to the best of their ability trees that showed beech bark disease resistance, but also certainly some of the work that Frederick's doing and others, looking at those trees that had at least crown forms that were resistant to ice, so looking for kind of U-shaped architecture where possible. So all of this to try to maintain this over time as a northern hardwood forest that's uneven. Moving into resilience, so again, this builds off of the resistance, so you'll see aspects of resistance in the resilience treatment, but then
We're also trying to increase the pathways for recovery in this forest back to a desired future condition, which is a northern hardwood forest, but just maybe containing a little bit more representation of other species. And so to do that, we need actually larger openings, so group selection, so 4/100th of a hectare to 1/10 of a hectare openings in 20% of the forest. So here's an example of one of those gaps. And the goal there is to recruit things like yellow birch, red maple, species that are at least projected to do better in the future on that landscape, and also a species like yellow birch that's also quite resistant to wind and other disturbances. So trying to increase how much of that's out there. Plus, if you work in northern hardwoods, you always want more yellow birch out there. Another part of this is actually retaining the forest in patches, so 20% just being left alone. So actually leaving behind spots that can be microrefugia for other species. And then again, I'm trying to kind of thin between these areas to give you that resistance component, so kind of building on that. Still increasing dead wood, so building on an ecological silviculture, and also again trying to favor those species that at least are resistant to wind and ice and so forth on that side. So finally, transition. So dealing with, again, uneven aged approaches, but now an irregular approach, so continuous cover, regular shelter woods. And in that case, I'm probably leaving, I keep forgetting I'm on camera here, leaving the screen. Creating gaps, but larger gaps. So in what we're doing in those gaps is actually planting tree species, so future adapted tree species, and I'll talk about that in a moment. But nonetheless, still retaining some areas intact and then thinning between. So we're reducing the overall stocking net stand, but we're still keeping a lot of that forest intact as we do this. So to show what this looks like from a LiDAR perspective, this is just a portion of this northern block through the eyes of the LiDAR. And don't ask me any questions. This is somebody else's work, so skip over it. No, this is somebody else's work. Evan Broadbent at the University of Florida has been using high-density LiDAR for this project. And this is the resistance treatment, so you can see just a lower severity, kind of diffuse pattern, so single tree selection. I apologize, it's orange, but this is the resilience treatment. Here's a landing, so that's not one of our gaps. We can see the gaps throughout the site. And then transition, so still the forest is there with these larger openings, and you can see within those openings we're retaining legacy trees, so deliberately retaining in cases like red maple, red spruce, also retaining any beech that has sign of bear activity on it. So using some of those historic approaches from an ecological perspective, but integrating it into our prescriptions. Then again, this is one of the beech that they deliberately felled for future dead wood on that site, or I guess it's current dead wood at this point. So the notion of future adapted, this is a term that we use when we describe kind of the change in forest conditions. And the main point that we use to determine what species, again, I don't like the terminology, or climate winners and climate losers, is this climate change tree atlas, which is a tool developed by the U.S. Forest Service. And so what you're seeing here, these are for some of the main species that exist on that landscape based on projections for the next 100 years, what are going to lose suitable habitat. This has nothing to do with migration, it's just suitable growing conditions. What might be currently on the site or in the region, but it's not going to see any change, so it might persist. And then what either is on the site in low abundance or isn't currently there, but is expected to gain future habitat on the landscape. So this is, those of you that think about northern hardwoods, a lot of our characteristic species are actually projected to decline in terms of suitable habitat on the landscape. So an important point about this as it relates to both these ideas of migration, so those of you that are more interested in just modeling species change over time and expecting oak to migrate through northern hardwood forests, but also as it relates to silviculture, more importantly, is that when we look at the actual average shade tolerance of those species that are expected to decrease, they tend to be tolerant trees, and those of you that know a lot of functional traits know that there's, not perfectly, but many intolerant trees tend to be more drought tolerant and vice versa for shade tolerance. So a lot of the species that are actually projected to increase over time are not very tolerant of shade. So if we're trying to actually introduce these into the forest, in many cases we're working against the natural ecology of that system, which is really to favor shade tolerant trees like hemlock, sugar maple, beech, and so forth. So what we really were interested in doing is understanding where is the natural niche for intolerant species in this forest. And again, I give credit certainly to Craig Lorimer at the University of Wisconsin, but also Patricia Raymond and other folks that have looked at this, that when we examine the niche of intolerant and intermediate tolerant species in these northern hardwood forests, it's these mesoscale disturbances, right? So windstorms, ice storms, forest tent caterpillar outbreaks, all of these events that aren't stand replacing, but certainly create these irregular, uneven age structures and openings that are wide enough to introduce them in. And so it's no surprise that our transition treatment really is based around irregular shelter woods, which are designed to emulate these mesoscale disturbance regimes, so building on that natural dynamic. So in terms of what we did for planting, we could talk for hours about how far superior Quebec's nursery program is to the northeastern U.S. Where I work and where most folks work, besides Irving, planting is not a normal thing, right? So there's very limited nursery stock, very limited nursery production. So we were limited to only using bare root stock. We didn't have an opportunity to look at containerized versus bare root seedlings, and also limited in terms of what we could use for seed zones. And so this is not a provenance trial. It's operationally what we had. We only planted the gaps. Again, remember thinking about the ecology of the forest. These would be the places where we might expect these intolerant and mid-tolerant trees to recruit. And when we selected these species, yes, there was a lot of climate projections, but we were trying to the best of our ability to match some functional redundancy. So, black birch, petulolenta for yellow birch, as well as thinking about species with higher quality litters, so Populus granitidentata or sugar maple. So trying to keep some of these species on the site from a functional standpoint. Likewise, we are disagreeing with some of the projections. So two of the species we're planting actually are expected to decline based on broad-scale climate projections. But we have a lot of local information about these two species and expect that they will see may do better on the site. And the main reason for keeping these on the site is we want to maintain a long-lived conifer component in that forest that had deep shades. We're trying to keep that functional condition. There's some bird biologists on our team that really wanted to make sure that was a part of what we did. A unique element to this is that we also planted B3, F3 hybrid chestnut. So these have been bred for resistance. Those were planted by nuts. Those are familiar with how you put chestnut out often, they've just been germinated, you bury them in the ground, and they do their thing. And then several species that are currently not on the site that you might consider assisted kind of range expansion for those species. So again, these will change in a year because they're one-year results in seedlings. We all know how quickly those change. But just to show you how things are shaking out initially, and again, I know we have a lot of time to talk today, so we can talk about why we're seeing what we're seeing on the site. But in terms of those species that had high survival, first overall, 74% is not fantastic. I'd probably lose my job as a reforestation technician. But it was a brutal year to plant. Those of you that can remember May, it was up to 32 degrees centigrade and dry, and so it was just not. People were in shorts in these pictures planting, so not a good time to plant, which again is a good data point for us as we go into these uncertain futures. But the species that tended to do quite well were a mix of both species found on site already, like red spruce, but also species like red oak and white pine and bitternut hickory that were moving onto that site. So we're seeing this mix of species doing quite well. Chestnut is way down here, and what this represents is actually germination, so the number of seeds that actually germinated. Those chestnut that did germinate actually are surviving quite well, and there's a lot of, I don't know what it's like in Quebec, but in the Northeast there's a kind of a cult around chestnut. People are very excited about chestnut, so they're very excited to see it doing well, and it's been a very snowy year for us, so hopefully they're being protected. Whereas black cherry did quite poorly. And that's a mixture of the stock was not high quality, and they were very small seedlings, and it was harsh planting conditions. So just to summarize this as it relates to future projections, before I wrap this up, the species that are doing best overall so far are ones that actually the climate models say are climate losers over the long term. And so what this really points to, and again, everybody in this room is familiar with this, there's a lot of system inertia as it relates to changing these forests, and in many cases, those climate projections and future species distribution models really show the major changes like 50 to 70 years out. Right? So for the next 50 years, a lot of species on the landscape are projected to still do okay. So what we're seeing is that right now, at least the first year, that those species that aren't supposed to do as well actually are doing the best, whereas those who are projected to do better in the future are actually not doing as great. So this just highlights some of the risk in planting based on future projections. Right? We're going to have to kill some seedlings if you really want to go full bore on this. I'm not saying you should or should not, but that's certainly a risk that you absorb. What you are gaining to some perspective, and this is where we often are looking a lot, and I know there's a lot of amazing work in Quebec on functional traits, and we always use their data sets, which is awesome to have those. Looking at how this is changing just a functional profile of these forests by planting. This is just looking at the community-weighted mean drought tolerance of the regeneration layer of these different treatments based on our field data. As you expect, the transition treatment, yes, now we actually do have a wider range of functional response in that community if these trees were to survive another 20 to 100 years. On the flip side, we're planting a range of species like white pine, hemlock, spruce. We're also planting things like big-tooth aspen. So we're actually reducing the typical specific gravity of that forest. So again, assuming that these trees live another 100 years, over time, the mitigation potential of this forest might actually be a bit lower, just based on kind of that lower average specific gravity, so lower stand level biomass. So just to finish, and again, I have to show diameter distributions because I work in silviculture. It's Philip will not let me leave if I don't do this. You've only seen it twice now. We have this is just looking at the number of trees across size classes. And the only reason I'm showing this is, again, to go back to my original point, that a lot of times when we think about adaptation and future adapted species, we have this current forest, and the goal is, well, now we have to kind of erase that template and put the new stuff out there, right? And so what I'm going to show is kind of how this forest has changed in response to this treatment. And what you'll see is that there's still a forest there that we're working with and integrating adaptation into that forest and working with that ecosystem, as opposed to fighting against what the natural structures are out there. So this is just what the control forest looks like. So the resistance treatment, when we implemented that, again, perfect marks for single tree selection. Really nice. They've met this target diameter distribution through their management. We look at the stand. We reduce the density across that stand. So again, thinking about increasing resources available to the residual trees, advancing that cohort so they have kind of uneven age structure out there, as well as the trees that we're leaving behind, selecting for resistance on those individuals, but across that site. Moving into resilience, so the stocking, so think about the area under here is how much stocking is out there. So the stocking is now lower, again, representing we now are putting gaps into that forest, so trying to create pathways for new species to establish, as well as to diversify the functional profile of that forest. But at the same time, we have this plateau, so we're actually carrying heavier stocking in these middle-sized classes, and what that represents is that we're leaving behind elements of that forest as permanent patches to try to retain that structure. And then finally, in between everywhere, we're thinning to kind of build on that resistance approach, integrate it into our resilience approach. So looking at transition, so again, the stocking is even much lower. So it's actually the average stocking across there is about 14 square meters per hectare. And what that's representing is we have these larger openings that are really giving us the opportunity to plant seedlings. Hard to see this, but this is a bitternut hickory. If you haven't ever planted bitternut hickory before, Caria quotiformis, huge like tuber-like rootstock, which is fantastic for keeping it alive even during droughty planting seasons. But even though we're transitioning that forest, a lot of that forest still remains, and we're using that remaining forest as a way to both keep complexity in that system, but also hedge our bets as to, if that hickory was the wrong choice, we still have seed sources, we still have mature forest structure and all those elements out in the landscape. So, as a few folks in this room already know, I am a big proponent for ecological silviculture and historic range of variability. But I'm also not naive in assuming that the world is going to stay the same. But when we think about integrating adaptation into our landscapes, particularly these mesic systems that we're not talking about Sierra Nevada forests in California where things are just could disappear tomorrow, and they have been disappearing. There's a lot of persistence and a lot of pathways for recovery inherently in these forests, the resilient systems. And so trying to kind of work with that versus work against it, I think, is really critical. And we kind of call this kind of planting functional enrichment, trying to bring some new traits into that forest, but still maintaining some of those ecosystem elements is pretty critical. And again, you can email me if I'm wrong, and all your forest vaporizes tomorrow because the models say they will. But I would suggest, and if you've looked at tree rings, even for a moment, you're amazed what a 300-year-old tree has lived through to persist on site. And so when we're working with these forests and recognizing the inherent variability and complexity of the trees that are out there, when we're developing our transition strategies, really doing it within the context of what's on the site, both because it makes a lot of sense not to fight against that ecology, but also, leaving trees is not a bad thing as it relates to drought, as it relates to biodiversity, as it relates to ameliorating some of these precipitation extremes that we might be getting. So using that retention, which was historically really a biodiversity goal, now using that from a perspective of climate amelioration perspective. All right. So a lot of folks contribute to this. This work. I certainly don't do much of my own, or don't do much. The other people do the work. Particularly a lot of the results from the New Hampshire site. Peter Clark is a PhD student with me, and Loic to Orangeville actually has been helping us with the precipitation manipulation experiment. And I'm happy to slow down and reiterate things I probably ran through quickly, but I didn't say anything about the Bruins, so that's good. All right. Good. All right. Questions, folks?
questions à la salle. Si vous êtes pas à l'aise de la poser en anglais, on pourra traduire pour vous. Est-ce qu'on a des questions? Est-ce que vas-y, Titre.
Thanks for the talk.
Yeah, again.
It just made me think a little bit more than the last time. I was just wondering, you said about mitigation that switching from a species assemblage where the mean specific gravity will be lower. I think it's much more complex than that.
Yeah, it is.
It's related to the soil sequestration, and also with the white pine, it's bringing like a superstory layer that make it able to pack much more carbon. So it would be important when, and the same for the big tooth aspen, which can store a lot of carbon because they are able to grow very fast and keep biomass for quite a long time still. And so I'm just wondering how this mitigation thing, is it something that you have thought a priori, or is it something that is coming after that you think about it? What was it an issue by the forester that were discussing about it?
Yeah, and I think that, and I totally agree with you. I mean, to your point, our highest biomass forests are stratified white pine, hemlock. I mean, just the packing, you can do those. So you're right. I mean, in terms of the canopy architecture, I agree that just looking at average traits is not a good way to get at that. The biggest concern, actually, the bigger trade-off, I think, is to get these species established, you have to disturb more biomass to do that. So in terms of kind of stand level stocking, and that was the bigger concern. So there's Rich Howarth is an ecological economist at Dartmouth. He's very interested in carbon, and so he's very interested. He's very excited about this work. But the further you get into kind of putting new species and in creating space for those species, obviously you're going to reduce stand level stocking and so forth. And so I think that's a bigger trade-off, less so with the change in species mix, but more in terms of disturbing kind of an intact canopy, which by default, we're going to lose on-site stocks there. Looking at the full life cycle, it might, depending on what the species mix is, it might still be not carbon neutral, but maybe less of an impact. So I think that's the bigger trade-off. And even with, like, if you want all carbon, which some folks are going, you could have, as you all know, like very dense stock stand, lots of beech or lots of red pine. That unthinned stand is like the best thing in the world for on-site carbon. But from an adaptation perspective, is extremely vulnerable, and the opportunities for introducing complexity into that system are quite low. And so we've been for a long time arguing, that there are some trade-offs just inherently between maximizing mitigation from an on-site perspective and then also integrating adaptation, just given you do need to disturb the forest to kind of introduce these pathways. But I think you're right. I mean, it's definitely not a simplistic. I mean, it's a very simplistic way of looking at just the actual community weighted mean trait value versus over time, what is that structurally going to look like, and what densities and so forth we have out there. We have done some very detailed soil carbon kind of mapping for the experiment. So the goal there again is to try to look at that aspect of it. And there's a lot of other things. I'm a tree person, but looking at even biodiversity trade-offs. So again, we're excited about adaptation, and I'm not simplifying it. I'm just speaking from the American perspective. It's been so focused on what trees go out there now, and it's like a very weird change from managing for ecosystems and managing for biodiversity, and now it's about trees. And so a big part of this study, there's a large small mammal, bird components to it, looking at kind of wildlife response. There's a soil moisture component to look at hydrologic dynamics. And so trying to bring in some of those other ecosystem values that we might be thrilled there's bitternut hickory out there, but if that's compromising habitat and some of those values, what does that mean? But to mitigation, I think, at least my perspective is just the disturbance severity axis is far more important than the species composition, at least in this context. So good point. Yeah.
I was curious if you could elaborate. Yeah, I don't figure that I'm interested in the climate relationship with the species.
Yeah.
Can you just maybe elaborate on what sites exactly? Was that on one specific site? Or
It was a landscape. Yeah. So we cored 36 different forests across almost there, northeastern Minnesota. So kind of what they call the Arrowhead region. And so these were natural stand. They weren't old growth. Some were actually were
pristine, but most of them second growth forests. And just like the work that we did with those experimental forests, we cored all the trees on the plots. And this actually, Jane Foster and then Malcolm Eider have both had some papers come out of this data set because we were dumb enough to core all the trees, so they're really excited to have full population level samples. So we then fit spatial temporal Bayesian models to predict growth. And so the model was, growth is a function of tree level factors, like size and age, which traditional dendrochronology would totally get out of the model. And not surprisingly, that explains like 97% of the variation in growth, which is why I think it's important to keep in there. We also looked at density and spatial pattern, and then climate variables. And so what we're looking at here is just for those parameters in the model, this is the posterior distributions for the temperature variables, because temperature did matter. So this is the distribution of kind of response within, black spruce is pretty narrow, which actually might be surprising to those of you that work with that species. We had a pretty low sample size for larynx, but some species like jack pine, we had a very large red pine sample size, so a huge range of response, in that within the species, and that's because we were keeping in the noise, which I think is important.
Is there a relationship with the ones that have really broad distribution, that they were distributed across the landscape?
Yeah, so
more than others?
What we found is counter to some of the other work was we didn't see a correlation between latitude. It was the species that had a very broad longitudinal distribution. So those species like trembling aspen, jack pine had very broad, and it makes sense, at least from a climatic, all of you know this, and actually Loic de Orangeville, that Nature paper showed this as well. He really saw east-west gradient, I believe, in the cores heated, because we're pushing up against the edge of the forest. So there's a very strong aridity gradient, across the range of these species. And so those tended to have much more variability, whereas, things like sugar maple, as well as red maple, they're just more of like a latitudinal distribution. There wasn't as much variation in the response. So on the landscape, yours is more probably on the landscape. Hardest, all of our our black spruce is a combination of both lowland black spruce and we did get on the Canadian Shield, so some of it was upland black spruce, and so we kind of captured the range of that species. But from a geographic scale, longitude was a better predictor of why certain species had wider responses to climate than again, some work's shown latitude is a better driver. But once you get, as you know, into the boreal zone, it's going this way versus north-south.
Were there some species where climate seemed to be more important than all the others?
Yeah, actually, good question. And some of the species, as you might expect, some of the lowland species, so both black ash, so Fraxinus nigra, black spruce, and tamarack or Laricina, they tend to have very strong, actually counterintuitive, although once you talk about it, it's not, droughts were good things for them, right? Because it was a better drained time period, and they had very strong signals associated with that in terms of sensitivity. But again, when we look at it in terms of everything that explains the growth of a tree, so much of it was just related to, is it a big tree, is it a small tree, is it an old tree or a young tree? And I think, again, and I'm not in dendrochronology, we often strip all that out and just say, this is the climate response to that species, but there's so much variation, and we sampled everything versus just like the isolated old tree to try to capture that, and that's why it's a bit more complicated.
Were there species where you had difference in response between big and small trees?
Yes, absolutely. And there's also, as you can imagine, very clean ecological data. Tons of defoliation by forest tent caterpillar. So what we were finding with Populus tremuloides, that depending on the age of the stand, once it reached that kind of vulnerable stage, so 20 to 20 years plus, where we'd see a lot of defoliation. Climate was very poor predictor. Really it was just the calendar year was a better predictor of growth. But in terms of small versus old, like with the shade tolerance, so sugar maple, and this is the edge of its range. I'm so glad to be living in the Northeast again. These trees are embarrassing as far as sugar maple is concerned. Very drought sensitive when it got to be a large tree. I don't think a lot about sugar maple. I mean, it's a sensitive tree, but out there it's extremely. We had 10 to 12 missing rings, on a 120-year-old sugar maple. So very, very extreme impacts on the mature trees, and it was often, once they became large individuals. Just just, it's the edge of the forest, you know, to the eastern biome, so it was pretty sensitive at large age, at older ages and larger sizes. You had a question?
Yeah, actually he killed two
Okay.
of my questions, but just yeah, I think it's a good point to make the selection of species based on their response at different stages.
Yes.
Because if you choose one stage to select your species, they might totally respond differently at the specific stage, or the survival is associated with other factors. So that's one point, but the last question I had is, I was quite surprised to see that the adaptive silviculture is basically the same silviculture we did.
Yeah.
So I'm surprised of this lack of novelty, and basically we are choosing the species a little bit more based on several factors. But I'd like to hear from you. There's no other ways to deal with that selection cutting, group cutting, and enrichment in big gaps.
Yeah, so at least again from the perspective south of the border, even planting in these forests is, people are, you know, so Bill Leake, who some of us is a legend, he was appalled by we wanted to do this experiment on, I'm glad we didn't because their soils are not half as good, but the Bartlett experimental forest, and they didn't want, you know, anything to do with it. You know, the idea, you know, we've for 100 years plus, we've relied on natural regeneration. That's, you know, low, you know, but if you go to the southeastern United States or the Pacific Northwest, and certainly even, you know, parts of Quebec and elsewhere, I mean, the discussion is more around, you know, selecting certain genotypes and even age plantations, and so culturally, you know, that's, and especially in the southeast, they're resetting that forest every 22 years, and you know, and so they can adapt and adjust very quickly, and they're also culturally, you know, comfortable with investing a lot up front and then, you know, recapturing that and so forth. So yeah, there's more extreme things we could have done, and even kind of tree level things we might have done to try to enhance resistance and resilience and so forth. But the goal is to make it operational and kind of, and so over time, maybe these aren't going to be enough to push the system. But when we looked at the arrangement even of those study sites, you know, they're all in fire dependent pine forests, where again, planting is often more common, and there's not a lot of, I'd say, inertia in those systems in terms of, you know, in terms of advanced regeneration. Our northern hardwood forests, you know, we're even, you know, beech is not listening. You know, you know, we're going to be fighting, you know, sugar. So there's a lot of momentum in that system against us trying to introduce things. And so our goal was to, you know, how do we work with that current system? And resistance can fail. You know, I mean, we keep trying and trying and trying, and then ultimately it fails. But from the transition standpoint, it's basically trying to introduce some of those species, some of those seed sources over time. Maybe in 100 years, it's a seed tree harvest, and those areas that we left, you know, actually planted, we're now relying on as a source of propagules. But in that landscape, clear cutting and planting and really pushing it, you know, would not be, you know, operational, and we just don't have the capacity. And it's very different, I know, once you get into Canada, Quebec in general. You know, your nurseries are a bit awesome, and in terms of land ownership and tenure, there's often more kind of budget to do some of these things. But in northern hardwoods, many folks are not willing to go too far on that. So it's part of the co-development part was how far would they go. And actually the managers got most excited about choosing trees because they always wanted this tree, you know, and actually the chestnut, the manager that did a lot of the work for us, that was kind of our bartering. He got to have a bunch of free chestnuts to put in his yard and so forth. But that's probably the most extreme thing we're doing is putting chestnut was not in that part of New Hampshire. But actually from a carbon standpoint, it's the ultimate tree in terms of growth and wood density. So, but yeah, and that's, I guess, the point of the talk is that at least it's kind of moving forward incrementally, understanding these systems they're still northern hardwood forests, and they're going to be northern hardwood forests for a while, and so working with it versus totally flipping a switch might at least be more operationally, and I think even from an implementation perspective, a lot more feasible.
It's just only also because we see good examples of resistance and resilience in all those forests.
Yeah.
So just looking at them and then understanding how they achieve this resistance and resilience might bring us some new processes to reproduce in the silviculture.
And even the mortar culture, the like adding extra dead wood, again, it was, these forests are not old growth, and so trying to bring back, from a seed, safe site for seeds, for trying to kind of for yellow birch, absolutely. And even there's the small mammal work is looking at truffle dispersal and then how that's influencing distribution of microbial fungi. So again, planting some of these species, I would imagine is going to be compatible mycorrhizal species in that landscape, but even some of those processes are trying to understand, how do those confer adaptation pathways that we might not be aware of. So, yeah, pretty boring. It's not revolutionary. Yeah.
But it's all in the tail of the tree marking regime. It's not that general treatment names that make it different. It's in the tail of the spacing and selecting how you use the subtle arrangement of stands in the space.
Yep, absolutely. And this area, again, similar to what your winter's still going on. There's probably maybe 50 to 60 centimeters still in the wood. I mean, it's a very wet part of it. And so red spruce is an example that it was selectively, just like a lot of this landscape, cut out of these forests. And so our climate models don't fully account for the true historic distribution of that species. But there's stumps everywhere, throughout this forest, and we've seen actually a downslope movement of spruce on the landscape. So our idea is, at least again, to try to capture. It's very wet. It's climatically, it's going to get warmer, but not to the point that it's going to stress. It's a temperate conifer. So, that might actually be shocking to a climate modeler. They don't like that we're putting it out there, but we feel like ecologically it makes a lot of sense based on the history of that forest. So.
I think it's all the time we have, but we will have time to continue the discussion. So thanks a lot.
Yeah, no problem. Thank you.
Just about that. Said about okay. Okay, we could increase it because it's fair wind. Or drought.
That's a great,
So what do you think? At the landscape level, what will you do for a while? For yellow birch, would you?
I keep it going. And again, that's just my you too. I mean, but I think the drought. Like the 40s.